you tell me the total volume of the solution formed when you mix two liquids, say for example 500 milliliter water and 500 milliliter ethanol? Here you can see the total volume is not 1000 milliliter, but less than that. Aren't you surprised to see this decrease in total volume? Next, calculate the total vapor pressure of the solution. Here you can recall Rolle's law to calculate the total vapor pressure of the solution. However, the observed vapor pressure and the vapor pressure as calculated from the ideal Rolle's law are not the same. Thus, it is observed that Rolle's law is also not obeyed. In this video, we will discuss the reason behind these observations. Let us start our discussion with the classification of liquid-liquid solution. On the basis of Rolle's law, liquid-liquid solutions can be classified into ideal and non-ideal solutions. We will first discuss ideal solutions. Here, you may recall the plot of vapor pressure versus mole fraction at constant temperature for an ideal solution. The dashed lines 1 and 2, as you can see here, represent the partial pressure of the components 1 and 2 respectively, and the total vapor pressure is given by the line 3. A solution, for example AB, which obeys Rolle's law over the entire range of concentration is known as an ideal solution. Hence, their graphical behavior will be the same as predicted by Rolle's law. And the total pressure P total will be equal to P10 plus P20 minus P10 into X2, where X2 is the mole fraction of solute. Now, we will see the molecular picture of an ideal solution. When an ideal solution AB is formed, then the intermolecular attractive forces present between molecules A and B will be the same as those between AA and BB. Hence, while mixing A and B, no heat is absorbed or evolved. That is, the enthalpy of mixing will be 0 for an ideal solution, and the volume of solution AB would be equal to the sum of volumes of the components A and B. This indicates volume of mixing also will be 0 for an ideal solution. Next, we will see examples of ideal solutions. In reality, a perfect ideal solution is rare. However, there are solutions with nearly ideal in behavior. Solutions of N-hexane and N-heptane, bromoethane and chloroethane, benzene and toluene, etc. behave nearly ideally. In real life, most of the solutions show non-ideal behavior. That is, Rolle's law is not obeyed over the entire range of concentration. The vapor pressure of non-ideal solutions is either higher or lower than that predicted by the Rolle's law. Thus, vapor pressure versus mole fraction plot produces curves rather than straight lines, as you can see here. Here the dotted lines represent the ideal behavior, these dotted lines, and the curved lines, as you can see here, represent the non-ideal behavior. If vapor pressure is higher, then the solution is said to exhibit positive deviation, and if it is lower, it exhibits negative deviation from the Rolle's law. These deviations are due to the difference in the nature of interactions at the molecular level. Let us learn this with an example. Consider a mixture of ethanol and cyclohexane. In pure ethanol, molecules are hydrogen bonded, as you can see here. However, in a mixture of cyclohexane and ethanol, these hydrogen bonds are broken because the molecules of cyclohexane will get in between, as you can see here. So ethanol can easily escape from the mixture than it was in the pure state. This will increase the vapor pressure of the solution and results in positive deviation. In general, you can say that A-B interactions are weaker than those between AA and BB. Then such solutions show positive deviation from Rolle's law. Or in other words, here the intermolecular attractive forces between the solute-solvent molecules are weaker than those between the solute-solute and solvent-solvent molecules. Consequently, both the enthalpy and volume of mixing are greater than 0. Next, we will see how solutions with negative deviations behave. Consider a mixture of acetone and chloroform. In their pure state, chloroform or acetone are not hydrogen bonded. However, in the mixture, chloroform is able to form hydrogen bonds with acetone molecules, as you can see here. In such situation, the escaping tendency of chloroform or acetone decreases and consequently the vapor pressure decreases. This results in negative deviation from Rolle's law. Thus, solutions where intermolecular attractive forces between AA and BB are weaker than those between A and B leads to negative deviations. Here both the enthalpy and volume of mixing are negative. If you look into the plot of vapor pressure versus mole fraction for non-ideal solutions, you can observe that there is a large deviation from ideal behavior at specific concentration, as you can see here. These large deviations results in another category of mixtures called azeotropes. Azeotropes are binary mixtures having the same composition in liquid and vapor phase and boil at a constant temperature. That is, at a particular composition, the mixture behaves as if it were a single component. Such a mixture cannot be separated by fractional distillation. Next, we will see in detail what azeotropes are. Azeotropic mixtures can be classified into minimum boiling azeotrope and maximum boiling azeotropes. The solutions which show a large positive deviation from Raoult's law or a maximum vapor pressure form a minimum boiling azeotrope at a specific composition, and those which show large negative deviation from Raoult's law or minimum vapor pressure, as you can see here, form a maximum boiling azeotrope at a specific composition. We may learn this through an example. Consider ethanol-water mixture formed by the fermentation of sugars. On fractional distillation, this mixture gives a solution containing 95.4% by volume of ethanol at 351.15 Kelvin. At this composition, both the liquid and the vapor have the same composition and no further separation occurs. At this point, the vapor pressure of the mixture will be maximum. Hence, this forms an example of minimum boiling azeotropes. Similarly, a mixture of nitric acid and water at an approximate composition, 68% nitric acid and 32% water by mass, the solution has a boiling point of 393.5 Kelvin. At this composition, the vapor pressure of the solution will be minimum. Therefore, this is an example of maximum boiling azeotrope. Have you seen pictures of salting roads during snowy winters in cold countries? The purpose of salting the road with sodium chloride or calcium chloride is to prevent the accumulation and freezing of snow on roads. Do you know the chemistry behind this? In order to explain the chemistry behind salting of roads, you should learn colligative properties. We will discuss colligative properties and their applications in the next video. With this, I will summarize this video.
Manorama Horizon. Learning made simple.